Alright guys, moving on to the next concept, which is of temperature and phase transition. So first let's talk about what is temperature, right? So temperature is a very simple concept, but most of us are a little confused when we are just starting chemistry. So I'll take some time to explain what temperature exactly means. We know how to measure temperature, right? We use a thermometer to measure temperature, but we have to have a clear understanding of what temperature is, right? So let's assume this is a particle, right? So this particle, whether it's in the solid state, liquid state, or the gaseous state, this particle is in a constant state of motion, right? So this motion gives the idea that the particle has energy. So you might have like studied in physics that anything that moves has kinetic energy, right? So this particle, which is in a constant state of motion, vibration, whether it's in the solid, liquid, or gas, has energy or enthalpy. So this is a fancy name that we use for energy, and it's denoted by H, and delta H here means the change in enthalpy, which we'll deal with in future lectures. But just for your information, energy, enthalpy, kind of like similar concepts. Anything that is in vibration has kinetic energy. That means it has enthalpy, right? So temperature is the measure of the average energy of the system, right? So, for example, if you have a balloon filled with a gas, right? So the gas, there are gas particles inside this, and each gas particle has its own velocity, has its own kinetic energy, right? Not all the particles will have same kinetic energy. So all these will have different kinetic energies. So if we measure the different kinetic energies, then get an average of those, that average kinetic energy of all the particles inside this balloon will give you the temperature of the system, in this case the gas. This can be true for liquids too. This can be true for liquids and the gases too, or solids too. Like you measure the average kinetic energy of all these particles, and the average is determined by the notion of a temperature, which is measured in degrees Celsius, degree Fahrenheit, or on the Kelvin scale. Okay, so here is an example of a histogram and a bell curve. Now, just for example, like in your class, if there are like 100 students and you take a test, and then you measure the number of scores, the number of students getting a particular score, and then you can get a histogram. Say, for example, the number of students getting a score between 40 to 49 is say 5. And then you measure the number of students getting a score between 50 to 59, all through 100, and then you make histogram. And then you make the bell curve by joining the midpoints of these columns, and then you get a curve. So that curve is called a bell curve, and bell curve is a particular shape which is called, the bell curve is the shape when we have a normal distribution. So it's a mathematical concept, normal distribution, in which we see these kind of like shapes. So we will study about these things in mathematics, but for here, just a short introduction, that whenever you have a normal distribution, you will have some people that have, so this is the average concept, this is the average number of your class. There will be some students who have the number which is below the average. There will be some students who will have number above the average of the class. But you measure all of them, you plot it, you get a bell curve. We'll do the same thing for the gases, for the particles in here, and we'll plot a bell curve. So for the first, we'll just see the white one, the white curve in here. So this shows all the particles with their energies, and then the average of these particles is denoted by the temperature, right? So the average energy is the temperature, right? Okay, so when you increase the temperature of the system, what happens? The average number shifts to higher numbers, and that is why when you have higher temperatures, the bell curve shifts towards higher temperatures, the average shifts. That does not mean that all the particles in that system has the temperature T2. That means that the average of that whole system is T2, right? So we have to keep this in mind, that in any system, when we measure the temperature, we are not just measuring the temperature. That does not mean that every particle has one kinetic energy. It's just a way of representing the average kinetic energy of the whole system. Some of these particles will have less energies, some of these will have high energies, and then it can be denoted by the average. All right? So that's that, and which brings me to the concept of absolute zero. So what's absolute zero? You might have heard about this concept, that 0 Kelvin is called absolute zero. Now, 273 Kelvin is 0 degrees Celsius or 32 Fahrenheit, right? So we will study about these conversions in a later chapter, but just for understanding what absolute zero is, this is the scale. The Kelvin scale is the scientific notation for temperature. So for the freezing point of water, it's 273 Kelvin, okay? Now, when you have more temperature, there's more energy and it's free to move, okay? So when you decrease the temperature, the kinetic energy drops and you have less temperature. So you have like less energy, it's less free to move, and it has therefore less and less temperature. Now, what will happen if you keep on decreasing the temperatures? So you have 273 Kelvin, you notch down, you put it in a freezer and you get it to say 200 Kelvin, okay? Then from 200 Kelvin you move even further down, 150 Kelvin to 100 Kelvin, and you will need a better and better freezer to do this, because not all freezers can get these systems to low temperatures. Now, say you have the best freezer in the world and you want to take the temperature of a certain system to 0 Kelvin. Now, is it possible? Now, we have to understand this, that this freezer, or this, like, say this balloon is kept in the freezer. Now, this freezer must be kept in a room, right? Like, you cannot keep it in the air, you have to keep it in a room. So, the freezer is in direct contact, like physical contact with the room. The room is in contact with Earth, like it is in a physical contact. So you are not able to isolate this system from Earth or from the adjacent, from any of these, from the room or from the building and things like that. So it is almost impossible, I will say, to make a system truly isolated, right? In order to get these to as low temperatures as possible. Because when you decrease the temperatures to these values, the heat which is supposed to go out of the system to freeze is now getting pulled in, right? Because this thing is in contact, right? So it is very hard to block this inflow of heat, and that is why you will never be able to get to 0 Kelvin. This is 0 Kelvin, not okay. So it is almost impossible to get to 0 Kelvin, right? Because you will not be able to isolate a system completely. So there will always be like inflow of heat in here. So getting to absolute zero is absolutely not possible.